Hello, my name is Michael, and I'm here to talk about auto tools, build systems, and software development. And so, this is a mid level discussion where we're not covering the basics, but we're also not going to the furthest fringes of advanced technique and explanation. So, what is software development? Because when we're talking about auto tools, we're talking about build systems. To me, that is a that is a topic that falls within the larger concept or the larger discussion about software development, right? And so you have your technical way of looking at software development, right? And then you also have your very basic way of looking at software development. The basic way is okay, you are writing code and you're building programs, right? And on the more advanced end of the spectrum, you're looking at algorithms, data structures, you're looking at DevOps, right? Well, somewhere in the middle, we're looking at, right, what is the real ground of software development? To me, software development is all about manifestation, right? So it's the manifestation of one's own imagination to affect change in this reality, right? And that may sound somewhat ethereal, or it may sound somewhat, you know, too general, right? But I think that captures what is really the heart of software development: manifestation of your imagination. I put it that way because majority of your software development is not cookie cutter, though some of it may look that way. Okay, so you could generally say that all e-commerce websites and web apps or mobile apps generally do the same thing. You could say that, right? But Amazon's mobile app is going to be different than Spotify's mobile app, right? They're going to be different, even though they do the same things. You have a listing of items, right? If you're doing Amazon Music, you have a listing of items, and you can look at the reviews on those items. You can select an item for purchase, put it in your shopping cart, so to speak, and transact the purchase and enjoy the content. Spotify, same thing. You got a list of tracks, you got a list of audio that you might be interested in, and you got the reviews. It's the same thing, but built by different people, different teams, and they have a little bit different structures to them. But on the outset, right, they basically look the same and do the same when you take away all the graphics design, the art, and all that sort of thing. So software development is taking something like that and bringing it into reality. The software developer, the person that puts a program together, they don't have a book that they can open up. They don't have an article on the web that they can look at and say, okay, start at step 1, and then by step 400, you have exactly this program for your use, right? Because even though they may find recipes on the internet or in books or ebooks that they get, they will find that their situation and their circumstances are going to be just different enough that they got to do some different things. So they have to pull from somewhere else. They have to pull from their imagination. They have to talk to people. They have to look at a variety of things and bring all of this in and synthesize it into a end result. So that's the big picture on software development, right? I'm looking down at my watch to make sure I'm still recording. So software code is normally thought of as C#, Java, Python, PHP. Those are all programming languages as we understand it. But the computer does not know those languages. The computer doesn't know C++. The computer doesn't know C. The computer doesn't know PHP. It doesn't know Java. It doesn't know C#. It doesn't know any of these languages that we all study and that we use, right? These are languages that living people understand and can put a blueprint together, put the structure of a program together, the sequence of the program together, right? And encode it in source code files, right? The computer does not directly understand those source code files. The source code then has to get translated into executable code. That executable code is then loaded into the computer's memory. And then the computer processor executes that code from the computer's memory, right? And so you're not putting C++ or C or Python or PHP in the computer's memory. What you are doing ultimately is that source code is then being mapped into assembly language and opcodes and microcode. So when that happens, the computer then executes those codes and produces a result. And so what C and C++ do, or how it differs in terms of the final result from PHP and Python, is simply that those executable codes are kept in a separate file. So you got your C, you got your C++ software source code, you got your source code that you wrote in a language that a living person can understand, okay, in a set of files. And then that gets translated, we call it compiling and linking, into separate files that the computer can understand, or files that hold code in a format that the computer can understand, right? Whereas with PHP and Python, it seems like those source files are executed directly, but there's simply a program called a Python interpreter or a PHP interpreter that is going to take that source code and translate it in real time directly into the computer's memory, into the RAM, into executable code, into the computer's memory and computer's RAM, that the computer can then execute and understand. So with that all out of the way, right, we all now understand what software is. And what we're talking about here is going from that source code to the executable code, and what is the process that we undertake as people that build programs, right? What is the process that we undertake to do that conversion? We've already written the code, the source code. We've already written the template for the program. Its blueprint is encoded in files, right? In the C++ world, we'll call those .cpp or .cxx files. In the C world, we call those .c files. In the PHP world, we call it .php files. In the Python world, .py files. In the Java world, .java files. And in the C# world, .cs files, right? Let's not leave out Visual Basic, .vb files, right? All of that is source code. The computer does not understand any of that. But we, as people that have studied the grammar and syntax of those languages, we understand those languages. So that it is a language that is a middle ground that allows us to talk to the computer indirectly through that mechanism we call source code. Okay. So, a build system is a set of tools or a mechanism that takes this source code and translate it into executable code files. The executable code files can then be given out to end users, given out to people, set up in app stores, set up as download links on the internet where people can download the program and run it directly, right? And so in the sequences that follow in this video, I'm going to first start in Microsoft Windows and look at the build process in Microsoft Windows, or at least the most popular way of doing that. Keep in mind, any of these examples that I show, there are dozens, if not hundreds, of other alternative examples that could apply, right? So I'm just highlighting the mainstream examples in the two cases that I show in terms of Microsoft Windows and Linux, right? The Linux-based operating systems. So now that we understand that, let's see what we can accomplish with build systems.
Just before the mid-1990s, my mother bought me my first computer, and it had Windows 3.1, which had a window called Program Files. And the present day Windows Start menu is very much like the Program Files screen. So icons such as for Microsoft Word, they are pretty much a pointer to the actual executable file. The executable file is going to be that file that runs the program, right? So let's take a look at what a executable file looks like in Microsoft Windows. So right-click on Word and I choose Open File Location, right? This is going to take me to the actual file on the file system. Here the file is actually named WinWord. That's the actual name of the program file for Microsoft Word. And so by double-clicking on that file, we see that Microsoft Word opens, and it's a very straightforward process. Do the same with Microsoft Visual Studio. Right-click on the icon representing Microsoft Visual Studio, and that takes us to a file named DEVENV. It stands for Development Environment. And so when you double-click on that file, it opens up Microsoft Visual Studio. Microsoft Visual Studio is the most used tool on Microsoft Windows for creating software programs. And so here I launch Microsoft Visual Studio, and I link it to a project I've been working on in Microsoft Visual Studio. Here we see a listing for Microsoft Word and its history. The history of the program Microsoft Word, it's almost 40 years old. We also see here that Visual Studio has a long history dating back to 1997. I got to use those earlier versions of Visual Studio, including Visual InterDev. Visual InterDev is a precursor to what you might call the tool set for Microsoft ASP.NET. Here we have Visual Studio 6.0, the box, the program, and it's on eBay now. At one point you could go into CompUSA and buy Microsoft Visual Studio right off the shelf. So it's a pretty cool box art, I think, and so I've always been impressed with that. Here on the left side of the screen we got the code window where all the source code is listed. By the way, this is the box art for Visual InterDev. This is the actual CD itself. I never quite made out what that what that artwork actually represents. This is a screenshot of Visual InterDev in the earlier days, and you'll see that it looks very similar to present-day Visual Studio. You got the File menu at the top, and you got the various menus along the bottom. And so the resemblance is quite striking, right? And so it just shows that the concepts have been in play for quite some time. So our focus is source code, executable code, and executable file, right? So source code is translated into executable code. And one way to replay that executable code is to have it in the form of a file. Here again we see screenshots of Visual InterDev and the earlier Visual Studio, and how similar that is to Visual Studio today. And so Visual Studio traces its lineage all the way back to those earlier programs. The process of writing source code in a development environment is a long established process, right? And so what I want to do here is I want to build the software. That is, I want to take the source code that's loaded in Visual Studio, and I'm going to use the menu item for building the software, which essentially translates the source code into an executable file. So I'm going to put this visual window side by side with the files on the file system. So we're going to go to where the files are actually produced by Visual Studio. Here there are 3 files. I'm going to delete all 3 of them and have Visual Studio recreate them. That's what a build system does. It takes your source code, your blueprint for how a program should be, and translates that into computer code, machine code that the computer can directly understand and execute. So we've regenerated the program files, and so that's why it's not really anything to do about losing the program file. As long as you have the source code, you can reproduce that executable. And so here's the program. It's running. The executable code is active, and it's pulling live images from the internet, and it's doing what it's supposed to as an executable in its executable form. So that is very good progress, and that is our major highlight into how that type of code is done.
Now it's time to see what this looks like in the Linux-based environment. So going to switch over to Fedora 37, the Fedora 37 GNOME desktop, and run a GTK program, a program that was written in C++ using the GTK toolkit, to see how that compares to the process in Microsoft Windows.
What you will see here is the end result of what I felt was a long process on January 14, 2023, where I spent approximately 8 to 12 hours getting this process worked out for the very first time. On the right hand side of the screen is the software code getting translated, compiled, and linked into executable code format. On the left hand side of the screen, I have the result of that process superimposed upon another terminal screen on the left hand side, where the configure script was ran to determine what were the runtime build requirements for building the software. And so those two processes are represented. So you can say on the left hand side, in the left hand terminal screen is configure, and on the right hand side is Automake. So this is the program after it's been built It's freshly built at this point. And so the executable code, the executable version of the source code is doing exactly what it should be doing. Fedora Desktop, I'm going to take a brief moment to say that I think Fedora Desktop in the GNOME variety reminds me of Mac OS. And that's not a bad thing. I like the way the GNOME Desktop has evolved and how it's come along. It's very stable. Haven't seen many issues with it. You got the main system menu at the top. And you got all your icons down at the bottom, just like on a MacBook or an iMac or Apple computer. And I think that's a good way to make these systems somewhat universal, in that you have the same concepts applied across the board. So let's do take a closer look at this RSS reader program that I built in C++, where I use 7 code libraries, right? And it's connected to the internet. And so it's not the most complex program in the world, but it does have some complexity to it relative to a very simple program. And so you could say it's a moderately complex program. And here is the executable file that was produced through the make files, through Automake, right? And so this executable file, it has all the instructions encoded within it that the computer can readily understand. So when you double click on it, just like double clicking its cousin over in Microsoft Windows, a program window emerges and it has content in it. And as I click through the lines of content, the display interactively updates. It interactively updates to show information from the left-hand side to the right-hand side. And there are various menus where you can tab through different islands of content. And this program updates from the internet in real time when it's connected to the internet. And it's also designed to run offline so that the lack of internet connectivity is not an hindrance to its operation. So everything is functioning as it should. The source code blueprint and template is properly designed, properly defined, and the implementation is solid. I'm able to click on an article that's represented in the program, and it opens up that article in the default web browser, where I can now go through the article in more depth, right? And so that's a very useful function of this program. And the C++ code that was written to accomplish this made use of WebKit. It made use of WebKit, which is the same framework that Apple uses for Safari. And it's been very useful in not only rendering HTML content in a window in a Linux-based program, but also to affect opening links and URLs from desktop programs. So quite a bit of potential here with WebKit. And this is the configuration screen that I also defined. And so I'm quite pleased with how this program turned out. And I can't wait to see how I'm going to evolve that now that I have a more productive way to build the software. And when I say build, that means translate it from source code to executable code where I can readily test it. As I was going through this process of understanding Autotools and how it fits into the overall software development process, I found it helpful to diagram it on paper. I often diagram software systems on paper because I find that kinesthetic and tactile process to be worthwhile. And when I really understood Autotools, when it started to click, I decided to write it on paper, and what that did is that encoded it in my subconscious. Because our brains are just like computers, right? Our bodies are like computers. I have encoded this into my mindset where I can understand it at a more intuitive and deeper level, which affects my ability to apply this technology more readily. And so let's look at Autotools at a mid-level.
So the sequences you just saw basically took the source code files that were written in C and C++ and translated them into executable files, right? So the executable files is what the computer actually understands. And these executable files, they number in three in this case. I have the Gaucher RSS newsreader, which is a graphical user interface program, right? That shows news articles and feeds. And I have news download, which is a command line version of the same thing that is used primarily for testing the underlying API that I put in place for this process. And then I got RSS IO test, right, which tests some of the more fundamental IO structures that I put in place to move data, from an HTTP endpoint into XML, and from then XML into a file. So some of these feeds would then be stored into a file or into an SQLite database. And so those IO endpoints need to be tested. And so this entire process of, let's say, translating software source code, in this case C and C++ source code, into executable file format, that can be scripted by hand. And indeed, um, the best thing that a person should learn is how to do compilation and linking on a command line, right? And you can script all of this, right? But scripts are all different. Everybody's script is different. There's not a standard way to write scripts in the same way that you might write certain types of software modules, right? If we're going to use design patterns, right, Gang of Four design patterns, and enterprise design patterns advocated by Martin Fowler, right, then yes, there are some standard blueprints that we can apply to conventional software. But for scripts, there might be some recipes out there. There might be um, some great examples on Stack Overflow or Stack Exchange or other websites. But by and large, scripts are far more diverse than your than different categories of software modules written in um, what you might call fourth generation programming languages, third generation and fourth generation programming languages. And so the scripting that you could do is a way of getting the translated process done. But by using Autotools, you basically adopt and apply a more systematic and structured scripting system to do the translation. And in doing so, you make your software process, you make your software composition more acceptable and more approachable to a variety of operating systems. So when you're trying to get software distributed and deployed to a an audience of, let's say, Fedora desktop Linux users, right, or Microsoft Windows desktop users, or maybe you want to deploy the software to servers, to Linux servers, and the software would work best if it came out of a Linux-based package management system, right? So those are not situations or opportunities where you want um, untested script, or what do we say, uh, less mature, less mature deployment vessels, right? And so Autotools provide you with a very structured and well-tested deployment tool and build tool, right? So the build is what we're really focusing on, but the structured and standardized nature of Autotools allows you to build your software consistently and integrate it with packaging systems for Debian, for Arch, for Mac OS, as well as Red Hat based systems such as what we called CentOS and um, Fedora and Red Hat proper, right? As well as SUSE and Manjaro. And so the wide variety of operating systems that exist out there and the particulars of how you get software integrated into those environments can pose a challenge to any single software developer who wants to deploy to all of those environments, or at least a more than one or two environments, right? Even trying to get software deployed between Windows and Linux. Let's just say you chose Ubuntu and Windows 10. Well, the deployment requirements couldn't be more different. And so a system like Autotools helps narrow the gap there so that it is you have to spend less time attempting to understand how to get software from Fedora into Ubuntu or from Ubuntu into Windows, right? You could take your single source code and with modifications to a well structured, well documented configuration system, get the software deployed to those environments in a much more productive way. So in the segment that follows, I'm going to go into more detail about this process. Like I said at the very beginning of this video, I'm not going to go so detailed that this is an advanced talk, but it's also not going to be like the previous videos or the videos that preceded this, where it's a more basic talk, right? So this is going to be right smack in the middle so that you get an idea of what Autotools is about and what I see as the usefulness of Autotools for everyday software development using C and C++.
I would like to start by deleting all the files in the build environment, in the build directory. The build directory is where the final executable code and executable files are to go. And so I have no qualms and no issue with deleting it permanently because all of the source templates are in the source environment. During this process, I had several manuals up. I had the Automake manual, the Autoconf manual, the Git manual, just in case I needed to do something there. I had several other screens open. So I have my command windows into two tabs. One for the source tree, where I basically use autoreconf-i as I make changes to the configure.ac file, as well as the makefile.am file, right? And so as I make modifications there in those two files, I run autoreconf-i, right? And then over in the build tab, I basically run configure followed by make, right? I throw a reset in front of those commands just to clear the screen and have clarity on where I'm at. So as I run make, in this case, run configure and then make, notice that on the left hand side of the screen, the build artifacts are being generated in real time, right? And so you get to see that process in a visual way in this interactive environment, in this interactive desktop environment. The object files are generated one at a time, and then they are composed together at link time into an executable format, right? An executable file. And the screen on the right gives all the details, the command lines that are developed by the make process. And so just as a rudimentary unit test, I launch Gaucher RSS, the executable file that was generated, just to make sure everything is what I expect it to be. And so go back to the desktop to switch into gedit, where I have copies of the different files loaded, the configuration files. I am perusing the original make file from Gaucher RSS version 7. We're now in version 8, which uses the new Autotools process, or the process new to this endeavor. And the original make file, you'll notice it's quite voluminous, right? For a file that is partially handwritten and partially generated. It was generated with Bakefile. If you've tracked me on my blog, you'll notice that Bakefile did not work out too well. But here is the makefile.am template, right? And this is the makefile definition that is then converted into a more in-depth and practical makefile. You'll notice that the abstraction that I have available to me here allows me to reduce the number of definitions for translating the source code into executable code. And I am very pleased with that result, with that outcome. This is far more manageable and much more productive than what I was doing in previous iterations, where I started out with handwritten scripts, then I used an automation assistant, an assistant tool like Bakefile, and then I've moved to Autotools proper, and I find that it has reduced the amount of modifications. This is the configure.ac file, which I have customized to a greater extent, wherein I've added AC checklib directives so that they can affect the addition of the proper library references in the link command line. So I have the proper libraries, and I was using package config, but I noticed that when I used checklibs, I can reduce my use of package config. I still use that for the C flags and the CPP flags. I find that useful to have those directives for all of the object files that are generated in this particular project. And then I have a section there at the bottom of this configure template where I am doing embedded resources using GNOME, the GNOME generator for that. And so the GNOME generator, I was previously running that as its own individual script in the previous version of this project. And seeing as how ac.configure or configure.ac is a script in and of itself, I thought I would incorporate the script into this process, and it has worked remarkably well. And so the individual lines that you see here, they are designed to make sure that the environment in which the software is going to be built is properly set up for building that software. That's critical. Making sure that we have all the right dependencies, the right libraries, that the headers are going to be sourced in the right way. You could do many of these things in a makefile, but it's actually more streamlined when it's done in a configure script like this, because then you can basically partition this build process into identifying all the requirements, and are the requirements being met properly in the operating environment, in the operating system? Are the right requirements there for even building the software? Because if they're not, there's no point in even making the attempt to build the software. So that's what these definitions establish, right? Once this configure.ac file is translated into an actual script that is relevant to the operating system and operating environment in which it runs, right? So that's what this is. It's basically templates that get translated into the equivalent of hand-coded script files, make files. So that's what we have here. And as I go through the file listings for the the source tree, that is where all of this, the software itself is defined, the build is defined, and then through parallel building, right? The Automake manual talks about parallel build, in which you can actually build the software in a directory that is different from where the source code is, and that keeps you from cluttering up the source directory, right? It can stay clean. It can remain as a source of configuration, and it's the collection of elements that define what the software should look like and how the software should be built, rather than incorporating both that and the tangible mechanisms for that materialize the software and defines the software as executable code. So I like to have those things separate, right? I like to have the object files and the executable files, the shared objects, the static libraries. All of that generated content should be in its own separate area of the file system, so that as you regenerate those elements, you regenerate those files, they in no way can accidentally collide with the source files and cause issues there, because not everything remains perfect all the time, and you could have a situation where you're trying to do a make clean where you somehow accidentally screw up your source tree. And of course, if you're using Git, then you can recover from that well enough. But why even, make that a necessity, right? So that's what we have here. And now that this process has been defined and my intense 8 to 12 hours is done, I can close out these manuals and I can close out this process. But I want to run this process one more time. So let's delete all the files, and let's run the configure and then make. And once that's done, let's launch the program. And when we launch the program, we're basically asserting, it's like an assertion at a macro level, that the build process itself is functioning properly and functioning the way that it should. I want to start by running configure. And what configure will do is check the environment for the proper requirements, and then run make. Make is going to execute all the proper compile and link steps and generate the executables that is seen and shown on the left-hand side of the screen. So once those executables are in place, once we have the proper executables, and in this case, I'm looking for Gaucher RSS, an executable named Gaucher RSS. And once that executable is there, I'm going to launch it. Running the executable is the way to verify that this process works the way that the way that we expect it to. And so we've run this software a couple of times, and so we should be quite familiar with the way that the software looks at this point. We're expecting a screen that's going to have headlines listed on the left-hand side and content that is on the right-hand side. And so there's our screen here, and it functions exactly as we've just stated, and that verifies the process. On the right-hand side, we see the result of various diagnostic messages that program was designed to emit in a command line environment if launched from a command line. And now here we have the source assets listed. This is the Git manual. I'll close that out as we get ready to bring this to a close. So the Autotools is a great set of tools for standardizing and streamlining the build environment and the build experience. And it definitely makes creating code in C and C++ a more productive process. And the fact that it's a well-established process means that we can put a tremendous amount of confidence in it and look forward to more successful software development endeavors with C and C++ using the GNU Autotools.
The use of Autotools is quite interesting, wouldn't you say? Um, I am actually pretty thrilled with the whole process overall. What do I mean by that? Well, I spent many years scripting this process by hand. Scripting this process by hand. And I was fine with that, but what I see is that as the years go on, I want to spend less time doing that and more time in the actual construction of the software itself, right? And that doesn't suggest that I spent more time um, in building the software, right? We're using the term build to mean the translation of the software into executable format. Doesn't suggest that I spent more time on that than constructing the software. But I saw barriers to productivity the more involved I got in that. And so when I finally saw how Autotools worked and I really got it, it was like, you know what? This definitely saves a ton of time, and it is still compatible with the way I see software development unfolding in my personal projects, right? My personal projects. This is not something that I would nominally do in other processes involving maybe teams or professional projects. But I do see this as a huge change for me in that it's going to accelerate the way that I can use C and C++. So I'm very thrilled about that. And more than that, I am happy and, let's say, pleased with the prospect of taking another look at the RPM and Deb packaging process to see what kind of productivity I can get in that process so that ultimately I spend less time, far less time, building the software and packaging the software and get to that place where I can have the software so well packaged that installing it in other environments is exceptionally trivial. Exceptionally trivial. So that's my goal for that and my hope for that. It is my intention that this will be my final video on Autotools. I think I've given a good amount of discussion on it. And so that's why I thought it was important to go into a little bit more detail, a little bit more depth on Autotools before I moved on to a different topic and another range of discussions. So I hope that this overview and this walkthrough has been illuminating and insightful. And as always, be well, be wise, and be healthy.